Okay, so in the previous class we have gone through the analysis of DC load line in case of BJT, DC load line for BJTs, and also how this DC load line is decided based on different operating points. Based on different operating points, we were deciding the DC load line. Like by connecting all the operating points for a given circuit, we can just get the DC load line, and this DC load line will be having two extreme points. Okay, so these two extreme points is defined such that beyond this it will be like the saturation. So this point is basically given by VCC divided by RC. This is the extreme point. That means beyond this, the saturation region of the operation will be starting. So in this region, this will be the region of active region, okay, or the linear region. Beyond this, it will be like the cutoff. So the saturation and cutoff, in between saturation and cutoff, this DC load line is defined, and this DC load line defines the active region operation of the BJT. Okay, so we have seen all this, and why this DC load line, or why the operating point or the Q point is required for proper operation of an BJT in terms of amplifier. So if BJT is working as an amplifier, then why it is required, like the operating point should be within this active region, and also to have a proper operation of the BJT as an amplifier, the operating point should be at the middle of the operating point. So whatever the operating point line is there, the middle of operating point will be the optimum or the most efficient operating point at which the BJT should be working, so that the amplifier should not be having any distortion. Okay, so based on the operating point of the BJT, we will be going with the different biasing conditions for defining different biasing conditions in case of BJT circuits. Okay, so here there are different types of techniques. Biasing techniques are there available in case of BJTs. So we will be seeing that the next, like what is different biasing techniques. Okay, so in different biasing techniques, so there are different biasing techniques, but we will be seeing the few. So first one that we will be seeing is fixed bias. Second is collector to base bias, and the third one that we will be seeing is self bias. Okay, so in the previous class we have also gone through like what is stability, how the stability is defined in case of BJTs, and this stability will be based on like where this Q point is operating. Okay, so where this location of the Q point is there. So whether a system or any circuit that is used as an amplifier by using BJTs, whether it is stable or not, we will be defining that. So that will be defined by the stability factor. In the previous class we have gone through. So the stability factor S is defined by del IC divided by del ICO. Okay, where VBE and beta, these two parameters will be a constant. We are just considering like because of temperature there is a variation in ICO. If ICO is varying, the current collector current will be affecting based on the ICO. So this variation is basically defined as the term S, that is stability factor. Okay, so in case of the common emitter case, we have just defined like the stability factor was given by 1 plus beta divided by 1 minus beta times del IB by del IC. Okay, so this was the formula that we have defined in case of common emitter case. So now we will see what is this stability value is there in case of fixed bias, collector bias, and self bias. We will just see like which of these biasing techniques are stable for biasing the BJTs. Okay, so this S for a stable system, the range of S is given by it ranges between 1 and 1 plus beta. If S value, that is stability factor value, is ranging between 1 and 1 plus beta, then the system will be considered as a stable system. Okay, so for a stable system, this would be the range of stability factor, that is S. Okay, so in all the cases like fixed collector bias, collector base and self bias, we will be calculating this S, and we will be seeing like how this stability factor is defined. So the first is fixed bias circuit technique. Okay, so here in case of fixed bias circuit techniques, the structure will be like we will be having a BJT that is connected with collector resistance, and here there will be a VCC. This VCC will be nothing but like it is going to have okay, so this VCC will be going to bias the collector side, and also the base side will be biased through the same. So this is the base resistance and this is VCC. So this is RB base resistance, this is RC, and here the emitter terminal is there, and at the collector we are taking the output. So output is taken as through a capacitor. Okay, so C1, these are called coupling capacitors. Okay, so that's why C1, CC2, these are coupling capacitors. Here V input is provided. So these capacitors, so beyond this, what Vi we have taken, this Vi is the AC input, basically the AC input we are providing. So AC will be only passing through this capacitor, DC will not be passing. So DC biasing will be provided by this VCC only. Okay, so to provide this DC, this is the complete circuit diagram in case of common emitter. So emitter is common between input, this is input side, and this is output side. Okay, so this is collector, this is base, and this is emitter. So emitter is common, so it is common emitter amplifier. Okay, so in this common emitter amplifier, Vi is the input, this is given by a coupling capacitor. Okay, and at the output, that is collector terminal, we are taking the output. So this output is nothing but the output through a coupling capacitor that will be only passing through passing the AC component. The DC component will not be passing through this. Okay, so all the AC component will be passing, that means AC output will be here, we will be getting. Okay, so this is the complete circuit. So on the input side, if we are going for DC analysis, this was the complete amplifier circuit. If we are going for DC analysis, so for DC analysis, the capacitors, whatever capacitors are there, that capacitors will be open circuited. So this capacitor will be open circuit. Why it is open circuit? Because capacitor does not allow DC. So for DC analysis, this capacitors will be like showing high resistance, so it will be open circuit. Okay, so because of their high resistance, this will be open circuits in case of DC analysis. The circuit for analysis in case of DC circuit will be the same. All the uh, capacitors will be removed, Okay, so if we are going for DC analysis, the circuit will remain like only this. This is RC, this is RB. Okay, so here we will be getting the output, but this basically this will also be an open circuit. Okay, so but we have just seen like from here we will be taking the output. Okay, so we can just remove it, so we can see. So this is your base terminal, this is emitter terminal, and this is collector terminal, and this is the direction of current is flowing. So here IE will be this way, IB will be here, and IC will be here. Okay, and the voltage between these two will be, this is positive and this is negative. So VCE, and this one will be the VBE. Okay, so we will go with the analysis. So now in case of this, suppose in the input side by KVL on input side, we can get from the input side. So here this is VCC, this is RB, and this is VB. So by going with the KVL, so VCC will be equals to whatever current is flowing. This is IB current is flowing. So RB IB plus VBE. Okay, so this will be the KVL equation. So from there, IB can be given by like IB equals to VCC minus VBE divided by RB. Okay. So in the previous class, we have seen by varying the VBB, that is base to emitter voltage, we were varying the IB current. So once we are varying the IB current, with respect to that, there will be variation collector current, and that correct collector current will be deciding the VC. So IC and VC will be operating point. So here also we need to set the VBB. So VBB is given by the VC directly. Okay. So and here the base current. So VB based on VBB, we are getting the base current. So IB will be decided by this. So VCC is going to decide the IB. So once IB is fixed, with respect to this IB, we will be getting IC. Okay, and with this IC, we will be getting the VCE. Okay, so here the IB that we are going to decide, this VC minus VB divided by RB. So when RB is fixed, VB is already fixed for a silicon type of BJT, that is 0.7 volt, and VCC is fixed, then the IB will be a constant value or a fixed value. So as IB is fixed, that's why this circuit is called fixed biased circuit technique. Okay, so here we are biasing the amplifier circuit basically by using a constant or a fixed base current. So once the base current is fixed, we will be getting some base current. With respect to that, we can get the IC, because this is common for common emitter. IC will be equals to beta times IB plus 1 plus beta times ICO. So once we know the fixed, we have the fixed IB, we can get the IC. So this IC for fixed IB, so this IB will be nothing but the IBQ, that is operating point Q. So for this IBQ, we can get the IC, that IC will be ICQ for IB equals to IBQ. Okay, so once we have the IBQ, we can get ICQ. Once ICQ we have, so at the output side, for by KVL at output side, we can get, so if we get the KVL at the output side, we can just see. So the KVL at output side is VCC will be equals to RC into IC plus VCE. Okay, so this will be the KVL at the output side. So here it will be VCC is equals to RC into IC plus VCE. So once we know the IC is equals to ICQ, we can get the VCEQ, that is Q point VCE value, that will be decided by VCC minus RC into IC, where IC is equals to ICQ. Okay, so we get from here ICQ, and from here we can get VCEQ. So once ICQ and VCEQ we can get the Q point. This will be your Q point, means at point at which the circuit will be operating. Okay, so so now our motive is to find the stability, that is S. So S is 1 plus beta divided by 1 minus beta times del IB divided by del IC. Okay, so from the above equation we have derived in the previous class also. So this is your stability factor value. So we need to find out the stability factor for this fixed bias circuit. So from there we can just get like, as IB is constant, we have seen like the IB is constant. If IB is constant, then del IB by del IC, that means for fixed bias IB is constant. So when IB is constant, del IB by del IC will be equals to 0 because this is constant. So by putting this to here, we can get S is equals to 1 plus beta divided by 1 minus beta into 0. So that is 1 plus beta. Okay. So here S is 1 plus beta. So stability factor in case of fixed bias circuit is 1 plus beta. If S is 1 plus beta, it is implies like this technique is an unstable technique. Like whatever biasing we are going to use, it is going to create an unstable system, because for stable system the S value should be ranging between 1 to 1 plus beta. So from here we can see for a stable system this should be the condition, but S value is 1 plus beta, so it is providing an unstable system. Okay, so we will see what is the advantage and disadvantage of this fixed bias circuit. Okay, so advantage of this fixed bias circuit is, here only one voltage source is used. Here we are just only using only VCC as the voltage source. Okay, so this is the advantage. In case of disadvantage, so the disadvantage of big fixed bias circuit is it basically provides unstable system. It is providing unstable system. And also another one is like, here the current is basically decided by, so here we can see if VCC is fixed, VB is already fixed, so it will be decided by the RB. So to provide IB is equals to in microamperes, because IB is generally in microamperes, so RB value should be very high. Okay, so we need to have high RB value. So RB value should be very high. This is the disadvantage in case of this fixed bias circuit. Okay, so RB should be very high. So this is one of the disadvantages of this fixed bias circuit. Okay, so this is the all about fixed bias circuit. The next we will see, so in the previous class we have seen the we were biasing the input side so that we are making a fixed, or we are making the IB value, we are calculating the IB value. Once we have calculated the IB value, with respect to that we were getting IC and VC. So that means to decide IB is the main motive. We are just going to decide IB. So IB can be decided like we were using a separate voltage source. So we can use a separate voltage source, but for designing a circuit we should be avoiding to use multiple voltage sources. So to avoid that, we are just connecting VCC with a resistor to provide the biasing to this input side. So this is called fixed bias circuit, but it is having the disadvantage like it is providing an unstable system. So we will be moving to the next system, that is second, that is collector base biasing. This is collector base biasing. Okay, so in this circuit, basically the circuit is like it is collector base biasing, means base is biased with respect to the collector terminal. Okay, so here this is RC, this is RB, and we are getting the output from here. Okay, so this is the complete amplifier circuit. So here we are having collector base biasing. Okay, so this is collector base biasing. So we are biasing the base terminal with the help of collector terminal. So this is your collector terminal, this is base terminal, this is emitter terminal. Okay, so this base is biased with the help of collector terminal. Okay, so that's why it is called collector base biasing. So what is the advantage and disadvantage, we will see. So this is the complete circuit in case of uh, the amplifier, but once we are going for DC analysis we need to remove this part. Okay, the like the capacitor will be open circuited. Okay, in case of analysis, while doing the analysis of DC analysis. So this is the circuit for DC analysis. So for DC analysis, capacitor will be open circuited. Okay, so capacitors will be open circuited. This will be the circuit. So now here we are going to uh, define the active region, like how the active region is will be defined. So for calculating the Q, for Q or quiescent point in active region, we can get like the equation will be like IC will be, this is common emitter case. So common emitter case, the IC will be given by beta times IB plus 1 plus beta ICO. Okay, suppose this is of course equation 1, and similarly to get the stability factor we need to find out the IC divided by ICO. Okay, so stability factor were IC del IC divided by del ICO, that is equals to 1 plus beta 1 minus beta times del IB divided by del IC. Okay, so this is equation number 2. Okay, so here we have considered BE and beta as constant. So if we consider the KVL at input side, so KVL at the input side, if we consider, okay, so if we consider the KVL at the input side, so it will be VCC So the current's direction we can just see. So this is emitter current, this is base current, the collector current will be so here. Okay, so this is base current and this is collector current. So current passing through this resistor, that will be both IC plus IB, because at this point this is the point where this is IB and here this is IC, so here current will be IC plus IB. Okay, so the IC plus IB will be flowing through this resistor RC. Okay, so if we consider the KVL at the input side, we can just write. So from there, the VCC will be equals to the current through the RC resistance, that is IC plus IB multiplied by RC plus IB RB plus VBE. Okay, so this is the KVL at the input side. So once we have got this, we need to separate it, like we need to separate in terms of IB separately and IC separately. We will be like writing VC equals to, so IB terms are this IB and this IB, so it will be RC plus this is RB. Okay, so RC plus RB multiplied by IB plus RC IC plus VBE. Okay, so to find out the stability value, we need to find out the del I by del IB by del IC. Okay, so here we need to differentiate it. Okay, so once we will be differentiating with respect to IC, so this will be 0. Here it will be RC plus RB del IB by del IC plus RC plus this is again a 0. Okay, so from there we can just get del IB by del IC will be equals to minus RC divided by RC plus RB. Okay, so this is like equation number 3. So by equation above equation of 2, that is for the stability, so equation 2 and equation 3, we can get the stability value, that will be equals to 1 plus beta divided by 1 minus beta multiplied by del IB by del IC, that is equals to RC divided by RC plus RB. Okay, so it is 1 plus beta divided by 1 plus beta RC by RC plus RB. Okay, so this is the stability value. Okay, so from there we can just get like, so this is 1 plus beta divided by this value. So this denominator value is something greater than 1. So whatever value will be there, that will be greater than 1. So if we are dividing 1 plus beta greater than 1 value, then the S will always be less than 1 plus beta. Okay, so if this is the case, then we can say the circuit is stable. Okay, so this type of biasing, in case of collector base technique of biasing, the system is stable. Okay, we can call it, this is an stable system. So here some points we can adjust, right? So here the stability, how the stability can be increased or decreased, we can just see. So here this is RC. If we consider the point, like if we separate it out, like we make S is equals to 1 plus beta. If we multiply this RC plus RB, it will be RC plus RB in the numerator, RB divided by RC plus RB plus beta times RC. Okay, so it is like 1 plus beta RC plus RB divided by RB plus RC 1 plus beta. Okay, so suppose RC 1 plus beta is very greater than RB value. If suppose this is the case, then we can get, like, if we put this uh, assumption into the circuit, we can get the S value will be equals to 1 plus RB by RC. Okay, so stability is basically, we can just see that stability is going to be decided by the RB and RC value. Okay, so it is implies like if RB is reducing and RC is increasing, then S value will be like decreasing, or the S value is going to decrease. That means S value is going to decrease means the stability will be high in that case. Okay, we can just write like if RB is going to be reducing and RC is going to be increasing, then S value will reduce. It is implies like S value, that is stability value, should be low by reducing RB and by increasing RC. So we need to design this collector base biasing circuit such that if we are going to have uh, S low, that means stability, because we need to have a stable circuit, then S value should be low. That means it should be ranging between 1 and 1 plus beta. So to reduce this S value, we need to reduce the IB and increase the IC value. Okay, so from there we can just say like the stability factor depends on, so RC is the user dependent parameter. Okay, that means we can say like stability factor stability factor depends on the load resistance, that is RC. That means it is an user dependent parameter is there, dependent. So it is user dependent. So RC is user dependent. That means stability is also user dependent. So user can define the stability of the circuit by changing the value of RC. So this is all about your collector based biasing. Okay. So next we will see like the third case. So here the third case is called self-biased circuits. So here in case of self-biased circuits, we will be considering uh, this as the circuit. Here at the emitter side, there will be a resistance, that is emitter resistance. Okay, and this is RC, collector resistance, and the base terminal will be biased by using a voltage divider technique. Okay, so this is R1, this is R2, and this is connected to here, and this will be your VCC, and we will taking output from here with the capacitor, that is coupling capacitor 2, and input will be provided by the coupling capacitor 1, that is V input. Okay, So this will be the circuit. So here again this will be the emitter current, this is base current, and this will be the collector current. But if we are going to decide the operating point, we need to do the DC analysis. So for DC analysis, CC1 and CC2 will be open circuited. Okay, so once CC1 and CC2 is open circuited, we can just remove this part. Okay, so this will be our circuit. This is for DC analysis. This will be the circuit in case of DC analysis. Okay, so here in case of DC analysis, we will go with the analysis of the circuit. So to have here, basically we need to find out the equivalent circuits in case of while we are deciding the input voltages here. So in case of uh, base or input side biasing, we need to find out the voltage here, like what is the voltage here. Okay, so this is the circuit, but for analysis purpose, what we will be doing is we will be representing its equivalent circuit or Thevenin equivalent circuit of this circuit basically. Okay, so another circuit is equivalent circuit is represented in the form of like an equivalent voltage and the resistances. Okay, so that will be of the form, this is RC, this is VCC. Okay, and on the base side, this R1 and R2, whatever its equivalent resistance is there, that will be represented by base resistance RB, and whatever voltage will be appearing at this terminal, this voltage will be represented by a voltage source that is called the Thevenin resistance basically. Okay, so its equivalent circuit we will be representing. So this will be of the form this here. So this is RB and this is VBB, and this VBB will be the Thevenin resistance, and this RB will be your Thevenin, sorry, this is your Thevenin voltage VBB, and this is Thevenin resistance RB. So this circuit is modified to its this equivalent form. So we need to just find out like what will be the VBB. So here by using Thevenin voltage equivalent, so VTH or the VBB value will be equals to the voltage divider technique. So the voltage at this terminal, like at this terminal, the voltage at this terminal will be given by the Thevenin equivalent of, or we can say the by using the voltage divider rule, we can get in terms of VCC. Okay, so here this Thevenin voltage equivalent will be given by like similar to the voltage divider. So R2 divided by R1 plus R2 multiplied by the voltage, that is VCC. So this will be your VTH, and similarly the RTS, Thevenin uh, resistance equivalent. So resistance equivalent will be the resistances, that is R1 and R2, two resistances are there. If the voltage, so to find out the Thevenin resistance, what we do is we need to make this voltage source zero. Okay, so whatever voltage source is there, that will be made to zero, so we will be making zero. So this resistance is also connected to zero, and this resistance is also connected to zero. So it will be like at this base terminal, this is base, so at base terminal both R1 is connected to zero and also the R2 is connected to zero. That means at base both are in parallel. Okay, so equivalent resistance, the Thevenin resistance, that is the RB will be given by like R1 parallel with R2. So that will be equals to your like R1 R2 divided by R1 plus R2. So this will be your Thevenin equivalent. So once we have reduced this circuit into in the form of its Thevenin equivalent, or this circuit, that is simplified one, is like more familiar than the above one. So we have represented in terms of a more familiar circuit. So now we will be applying uh, the transistor action, like for active region. For active region of operation, the IC will be given by IB times IC will be equals to beta times IB plus 1 plus beta times ICO. Okay, so this is equation number first. Now the stability, for the stability it is 1 plus beta 1 minus beta times del IB by del IC. Okay, so now we need to find out the del IB by del IC. Okay, so by KVL at input side. Okay, so by KVL at input side, we have seen like at the input side we have represented in terms of Thevenin voltage equivalent and the resistance equivalent. So by using the KVL, that will be like VBB will be equals to whatever current is flowing, that is IB multiplied by RB plus VBE plus, along with that there will be a resistance in the collector side also, or emitter side also. Okay, so this will be the IE and this is your IB and this is your IC. Okay, so from the input side this will be like VBB will be equals to IB into RB plus, this is the base to emitter voltage, this is positive and negative, and this will be the emitter current multiplied by emitter resistance also. Okay, so voltage drop will be because of this also. So from there, so it will be plus IE into RE. So this will be the input side. Okay, so from there we can just get like VBB is equals to IB. So from there we can just represent like how this two values will be there given by in terms of these two. Okay, so this IE, we know like IE is equals to IC plus IB. Okay, by using the KVL, the KCL, that is current equivalent circuit. KCL, we have this at the junction of three different terminals of the BJT. This IE is equals to IC plus IB. Okay, so by putting this value here, we can get IB RB plus VBE plus IC plus IB multiplied by RE. So we can just separating it out the IB. So RB plus RE separated for IB plus VBE plus IC RE. Okay. So now we will be differentiating it because we have separated IB and IC. So now we will be differentiating it with respect to IC. Okay. So if we differentiate it with respect to IC, it will be 0, and then here RB plus RE del IB by del IC plus 0 plus RE. So from there del IB by del IC will be given by minus RE divided by RT plus RE. RE divided by this. Okay. So this is equation number 3. So as this is a negative circuit, negative. So del IB by del IC. So if del IB by del IC is negative, if del IB, or differentiation of del IB divided by del IC is negative, then we can, then if del IB by del IC is negative, then the circuit is stable. By putting this value, we can get the stability value, that is S. Okay, value will be 1 plus beta divided by 1 minus beta times Re divided by Rb plus Re. Okay, so always it will be 1 plus beta, 1 plus beta times Re divided by Rb plus Re. So it always less than 1 plus beta. It will be, because this terminal is more than 1, so it will be 1 plus beta will always be less than, so S will be less than 1 plus beta. That means the system is stable. So it means system is stable. Okay, that means this type of biasing is also providing a stable system. And how this will be depending, S will be depending on, so now we will be just making the separation by putting this like 1 plus beta Re will be, and Re will be separated, so it will be 1 plus beta times Rb plus Re, like in the previous one we can get Rb plus 1 plus beta Re. Okay, so here suppose if Re 1 plus beta is very greater than Rb, if this is the case, then stability factor will be depending on 1 plus Rb by Re. So again, if we need to have the stable system, okay, so as this Re in case of this BJT circuit is independent of user, basically this Re is not decided by the user, only the IC, that is load resistance, that will be defined by the user. So then the circuit stability can be controlled by the voltage drop across the Re only. Okay, so this Re is an independent term for the user, then the stability of the circuit can be controlled by the voltage drop across the Re, and this is also an independent term for the user. So ideally in case of uh, uh, amplifier circuits by using the BJTs, ideally if we talk about the IE value, ideally Re value is considered to be infinite. Okay, then we will be putting here, then it is said like the S value will be equals to 1. Okay, so if S is equals to 1, basically this is not possible, like this is ideal one, but if it is ideal one, then S will value will be 1, but ideally this is not, in practical case this Re is not infinite. Okay, so for practical applications, Re is high or Re is increasing, or and if Rb is decreasing, then S value will be decreasing. That means to get an, that means the system will be stable. That means if we are increasing the Re or we are decreasing the Rb, then the system will be any stable system. Okay, so from there we can get this as the concept. Okay, so this is all about the biasing techniques in case of BJT. So this biasing is required to provide a stable or an operating point that comes within the middle of the load line. Okay, so biasing is important for BJT circuits, and also it should be provided by different techniques. So few of the techniques we have just seen. So these are the three different techniques that will be decided by the different biasing, and this will be deciding the different operating points. So out of this, the first one that we have considered, the fixed bias circuit. So that fixed bias circuit was an unstable system. Okay, so it was providing an unstable system. So we should be avoiding the use of that, and even if the numerical problems are there, then we can go with the concept like how we will be analyzing the circuit. So we will you can just see into the numerical questions. So these are different three methods for biasing the BJTs. Okay, so the next topic, that is uh, JFETs or the MOSFETs, we will see into the next class.